Hello everyone, I'm Nitin Reddy from EC department. My topic is analytical design of PID controllers. Introduction. PID stands for proportional integral derivative. The usefulness of PID controllers lies in their general applicability of most control systems. In particular, when the mathematical model of the plant is not known and therefore analytical design methods cannot be used, it controls prove to most useful. In this field of process control systems, it is well known that the basic and modified PID control schemes have proved their usefulness in providing satisfactory control. Although in many given situations they may not provide optimal control. It is interesting to note that more than half of the industrial controllers in use today are PID controllers or modified PID controllers. Because most PID controllers are adjusted on site, many different types of tuning rules have been proposed in the literature. Using these tuning rules, delicate and fine tuning of PID controllers can be made on site. Four modes of controllers. Each mode of control has specific advantage and limitations. On-off control, proportional, proportional plus integral, proportional plus derivative, proportional plus integral plus derivative. On-off control. This is the simplest form of control. Proportional control. In proportional mode, there is a continuous linear relation between value of control variable and position of final control element. Output of proportional control is Cp of t equal to Kp into E of t. The transfer function can be written as Cp of s by E of s equal to Kp. Proportional controllers. As the gain is increased, the system responds faster to changes in set point but becomes progressively underdamped and relevant unstable. Proportional plus integral controllers. Integral control describes a controller in which the output rate of change is dependent on the magnitude of the input. Specifically, a smaller amplitude input causes a lower rate of changes of the output. Integral signal is sum of all instantaneous values, so when integral and proportional terms are added, the movement gets accelerated towards the set point. The major advantages of integral controllers is that they have a unique ability to return the control variable back to this exact set point following a disturbance. Disadvantages of the integral controller mode are that it responds relatively slowly to an error signal and that it can initially allow a large deviation at the instant the error is produced. This can lead to system instability and cyclic operation. For this reason, the integral controller mode is not normally used, but is combined with another control mode. Proportional plus integral control. Cpi of t equal to Kp of E of t plus Ki into integration of E of t into dt. And Cp of t equal to Kp into E of t plus Ki integration of E of t into dt. The transfer function can be written as Cpi of s by E of s equal to Kp plus Ki into 1 by s. In the proportional plus derivative control, and the equation is Cpd of t equal to Kp into E of t plus Kd into differentiation of Et. And the Cpd of t equal to Kp into E of t plus Kd into differentiation of Et. The transfer function can be written as Cpd of s by E of s equal to Kp plus Kd of s. Proportional plus derivative control. The stability and overshoot problems that arise when a proportional controller is used at high gain can be reduced by adding a term proportional to the time derivative of the error signal. The value of the damping can be adjusted to achieve a critical damper response. The higher the error signal rate of change, the sooner the final control element is positioned to the desired value. The added derivative action reduces initial overshoot of the measured variable and therefore adds in stabilizing the process sooner. This control mode is called proportional plus derivative control because the derivative section responds to the rate of change of the error signal. You can think of derivative control as a crude prediction of the error in future based on the current loop of error how far into the future. The characteristics of PID controllers: CL response, rise time, overshoots, setting time, SS error. KP is in rise time decreases and in overshoot increases. In settling time, small changes, SS error decreases. While in compared to CI, rise time decreases, overshoot increases, settling time increases, SS error eliminate. In KD, rise time small changes, overshoot decreases, settling time decreases, error SS error small change. Tips for designing a PID controller. Obtain an open loop response and determine what needs to be improved. Add a proportional control to improve the rise time. Add a derivative control to improve the overshoot. Add an integral control to eliminate the steady state error. Adjust each of the KP, KI, and KD until you obtain a desired overall response. Lastly, please keep in mind that you do not need to implement all three controllers into a single system if not necessary. For example, if a PI controller gives a good enough response, then you don't need to implement derivative controller to the system. Keep the controller as simple as possible. Thank you.